Hello, my name is Morris Yao, and I'm here to talk about linear regression and contextual bandits with HUBER-contamination. This is some joint work with Ankur, Moitra, Frederic, Koehler, and Sitan, Chen. So, first we'll talk about our motivation. So our motivation is the robust online regression problem. So what is robust online regression? Let's fix an unknown regressor, W, in RD, and we consider the following game. At each time step t, an online learner is presented with an arbitrary xt in RD. The online learner outputs a prediction, y hat t, in R. Nature reveals an uncorrupted yt, which is equal to w inner product xt plus some noise with probability 1 minus eta, and otherwise reveals an arbitrarily corrupted yt. The online learner's goal is to minimize yt minus y hat t whole squared for all the uncorrupted rounds. So this is a model of linear regression that is online that also has outliers, because with probability eta, nature could have introduced an arbitrarily corrupted yt. So what do we know about robust online regression? We know that the class of convex M estimators perform provably suboptimally on the uncorrupted rounds. We seek a robust estimator with good performance. Now, since the features xt are chosen by nature arbitrarily, we need a robust estimator that succeeds without distributional assumptions on x. And it is these two aspects that make our work different from the previous work on robust regression. So our primary contribution in a sentence is we have the first efficient algorithm for online robust regression achieving optimal mean squared error. So the rest of the talk is not going to be about online robust regression, but actually offline robust regression. And we will show that the online problem reduces to the offline problem. And for these details, you can look in the paper. So what is offline HUBER-contaminated linear regression? It's a classical topic, and we don't have time to go into all of the techniques that are used to try to solve this problem. But the basic idea is that you have a regression setup, and some fraction of your data is corrupted. So what is our precise model? Our precise model is that HUBER-contaminated linear regression is the standard linear regression setup, but where a random eta fraction of the responses are arbitrarily corrupted. So let x1 to xn be the covariates, and let w be a regressor, and let y1 through yn be equal to x inner product w plus some standard Gaussian noise. And we adopt the scaling that the covariates xi are in the unit norm ball, and the regressor w is in the R norm ball, so that the labels, or responses, yi, are between negative R and R. And the noise is going to be standard Gaussian normal 0 sigma squared. A random eta fraction of the responses are arbitrarily corrupted. So you flip a coin, and with probability eta, you hand the response to an adversary, and they change it to whatever they want it to be. We are presented with the entire data set, and we want to recover W, the ground truth. More succinctly, let y star equal xw plus zeta, where zeta is normal 0 sigma squared. We form a data set for the responses, where yi is equal to yi star with probability 1 minus eta, and it is arbitrary otherwise. The algorithm observes x and y and wants to learn w. Our objective is to output a w hat, an estimator, with low mean squared error over the uncorrupted noiseless labels, because there's no point trying to predict the outliers. So what does this mean? It means that we want to minimize the objective 1 over n times summation over all I of the difference between our prediction, w hat inner product xi, and w inner product xi whole squared. So that's the difference between the blue point and the orange point. So I hope that makes sense. Now, this is the clean mean squared error. It is equivalent to w hat minus w inner product xi whole squared over the entire data set. So that's the objective we're trying to minimize. And we're trying to get it to degrade gracefully with the corruption level eta. Now, what can we even hope for? And what bounds do we achieve? So the upper bound is provided to you by, say, ordinary least squares. It achieves a clean mean squared error of eta r squared. And the lower bound is that no algorithm can achieve a clean mean squared error that is better than eta squared sigma squared. So how different are these two bounds, right? So what is eta r squared? So if eta is like a constant, and if r is, large, then we actually haven't done much regression at all, because the amount of error we're making scales with the entire range of the values y can take. So remember that r is, y is bounded between r and negative r. So if you're making r squared type error, then you're actually not doing much regression at all. And the lower bound is that you can't do better than eta squared sigma squared. So if sigma, the noise variance, is much smaller than r, the entire range of the values of the responses, then you can do a lot better than this naive upper bound via ordinary least squares. So what we're going to achieve is this eta squared sigma squared bound up to constants. And so just to belabor this point, we think of these as being very different. So perhaps it's better to just illustrate with an example. If the noise variance sigma is approximately the same size as r, then we're in the setting on the left. And if sigma is much smaller than r, then we're in the setting on the right, where the noise variance is much smaller than the range of the data. Now, when we add outliers, we see that on the left, the band of optimal clean mean squared error predictors, they are, they actually aren't, they don't provide you with a very good regression, because there's not much regression to be done. And when sigma is much less than r, then this is the setting in which regression is meaningful. So we think of sigma as being less than r, and that's what we're going to try to achieve here. We're going to try to achieve eta squared sigma squared clean mean squared error. Cool. So our main theorem is there's an efficient algorithm for HUBER-CONTAMINATED linear regression getting clean mean squared error O tilde eta squared sigma squared, which is optimal up to log factors. We also have an extension of our results to online robust regression and also to the contextual bandit problem, and we would point you to the paper for these sorts of details. Now, what are some existing approaches for the offline HUBER-CONTAMINATED linear regression? Well, there are some classical approaches like least absolute deviations and Huber's M estimation. So what is least absolute deviations? It's just L1 regression, and Huber's M estimator, which is some variation on L1 regression. And then there are approaches like least trim squares, which we will talk about in detail later. And then there are sum of squares and filtering approaches, which have been very popular lately, to deal with corruptions both in the responses y and also in the covariates x. Now, what unifies these approaches is that they only work under strong assumptions on the distribution of x, and they provably fail otherwise. And this is a problem for us, because in our setup, there are no distributional assumptions on x. So perhaps a prototypical example of a result in this area is a theorem by Chino that says that L1 and Huber regression succeed in getting an optimal clean mean squared error of eta squared sigma squared when the covariates xi are drawn from a distribution d that is hypercontractive, which is to say, for all directions, the fourth moment of x, expectation of u inner product x to the fourth, is upper bounded by some constant times its second moment squared. Now, what this means is it's some notion of spread in every direction. Now, we don't have this in our setup, and that's going to be the primary difficulty in what we are trying to do. And yeah, of course, not every distribution is hypercontractive. For example, the Bernoulli distribution is not hypercontractive. And we want robustness without strong assumptions on the data. Cool. Also, as a side point, covariate outliers cannot be removed without hypercontractivity. So it is necessary to have this assumption of hypercontractivity if you were working with X corruptions as well. But that is not the setting we are working with. So to talk about our algorithm, we have to first talk about least trim squares, because our algorithm is built on top of least trim squares. And we're going to take an optimization viewpoint. So let F be the set of all 1 minus eta n size subsets of the data. And consider the optimization problem. Minimization over all subsets S in F of the objective, summation over all I in S, and we're also minimizing over all regressors W hat in the R norm ball of the difference between Yi and inner product W hat Xi whole squared. So hopefully that makes sense. This seems like a natural approach, but it is intractable and could even have spurious global minima. So for starters, you'd have to enumerate over all 1 minus eta n size subsets of the data, so that's not efficient. And even if I could solve this problem, it's not clear that this is the solution to getting optimal clean mean squared error. So it seems like there are a lot of difficulties. At any rate, if I were to try to solve the optimization problem of least trim squares, then I would need an algorithm, and the canonical algorithm is alternating minimization. So what is alternating minimization? Let S be initialized to be the set of all points, and we repeat the following procedure. We construct an estimator W hat, which is just going to be ordinary least squares on S. And then we update S to be the set of points with the smallest residuals under W hat. And we keep on iterating this over and over and over again until we aim to solve the optimization problem of least trim squares. Now, this is not guaranteed to solve the problem, clearly. But, analyzing this algorithm is also a contribution of our work. Cool. So what is our algorithm? Our algorithm adds just a single additional constraint to the least trim squares optimization solved with alternating minimization. So what is this extra constraint? This extra constraint allows us to let F be a carefully designed family of 1 minus eta n size subsets of the data. So it's not all 1 minus eta n size subsets of the data. And how is it different? It's different because of the constraint at the bottom of the slide. Summation over all I in S, xi transpose, is PSD dominating 1 minus eta times summation over all I, xi transpose. So what does this mean? It means that the subsets S that we're working with, the covariance of S has to, in a way, subsample the covariance of the entire data set. And that's going to turn out to make all the difference. So perhaps to get some intuition for why this makes sense, we should first at least argue that this constraint is feasible. And so for now, we're going to introduce some indicators, AI, I going from 1 to n, that is going to indicate whether a point is in S or not in S. So AI is 1 when a point is in S, and AI is 0 when it is not. So our objective is then to minimize summation over all I, AI, yi minus inner product W hat xi whole squared, subject to AI being in 0, 1, and the summation over all the AI being greater than 1 minus eta times n. And we also need the most important constraint, that summation over all I, AI, xi transpose, PSD dominates, 1 minus eta, summation over all I, xi transpose. That is to say, the covariance of the points in S has to subsample the covariance of the entire data set. And why is this feasible? Well, because the ground truth satisfies it. So let AI star be an indicator for whether round I is uncorrupted, which occurs with probability 1 minus eta. Then due to matrix Bernstein, it's clear that this subsampling constraint is true, provided that n is large enough and adjusting eta slightly for some concentration. So clearly this is true of the ground truth because the AI stars are just Bernoulli 1 minus eta random variables. Now let's develop some intuition for why this is a good idea with a toy example, and compare least trim squares to our algorithm and show why our algorithm will avoid all the suboptimal minima of least trim squares. So here we have a standard linear regression setup where we have x on the x-axis and y on the y-axis, and we have 3 clusters of points. And we add some outliers in orange. Now, what least trim squares in our algorithm does in the beginning is it sets S to be all the points. and which are highlighted in green. And what least trim squares does is it updates the set of green points. First, it runs ordinary least squares to build this estimator in the yellow line, and it updates the set S to be those points with the smallest residuals with respect to this yellow line. And so it's going to be these green points here in the center cluster. And if we iterate this over and over and over again, we're going to find that these green points then, kind of bias the estimator again, and the estimator then sort of, reinforces finding these green points, and eventually we realize that we're not actually doing very well because we've completely ignored the cluster on the bottom left corner and the cluster on the top right corner. And that's really why least trim squares fails. Now our algorithm is going to avoid this pitfall, because after we come up with W hat, which is our ordinary least squares estimator, we update the set S, and it's going to include not only some points in this middle cluster, it's also going to include points in the bottom left cluster and the top right cluster. And the reason for this is because of this subsampling constraint. It enforces that the covariance of the points selected by S is it subsamples the covariance of the entire data set. And that's why this works, and that's the key point. Cool. So, how do we get this to work efficiently? Well, you can't let AI be Bernoulli 0, 1, so instead we're going to let the AIs be between 0 and 1, so they're going to be soft weights. And again, the summation over all these soft weights, AI, has to be greater than equal to 1 minus eta times n, and our minimization will be taken over all A and W hat of summation over all I, AI, YI, minus inner product W hat and XI, whole squared. So it's a weighted least squares minimization. To solve this minimization, we're going to use alternating minimization, which is a method to find first-order stationary points of the above objective, or indeed any biconvex optimization. And our algorithm was just to add this one more constraint. Once again, summation over all I, AI, XI transpose, PSD dominates, 1 minus eta, summation over all I, XI transpose, which is that the weighted covariance matrix subsamples the covariance matrix of the entire data set. Cool. So alternating minimization, again, what we do is we set AI to be 1 for all I to initialize, and then we repeat the following iteration over and over again. We let W hat be the argmin of the summation over all I of the weighted least squares objective, and then we update S to be the argmin over all A in the carefully chosen subset F of the weighted least squares objective. And this is a simple semi-definite program, and it's a semi-definite program because F has the semi-definite constraint that is the subsampling constraint that is, again, summation over all I, AI, XI transpose, which PSD dominates 1 minus eta times summation over all I, XI transpose. And that is the key. Cool. So once you add this constraint, you can dodge the spurious minima of least trim squares, and we can prove that with high probability, and provided n is greater than some polynomial in D and R, all approximate first-order stationary points AW hat attain clean mean squared error O tilde of eta squared sigma squared. So that's our algorithm. And a first order stationary point is that A is optimal given W hat and W hat is optimal given A. And that's all it takes to prove our main result. So we're not going to have time to provide the proof, but we have some time to summarize and talk about some future directions. So we provide the first efficient algorithm for Huber-contaminated offline and online linear regression with no distributional assumptions on the covariates and achieve information theoretically optimal mean squared error up to log factors. Now, the advent of distribution-free robust regression enables the design of robust algorithms in settings where strong distributional assumptions are inappropriate, which is key for applications in robust sequential decision-making, for example in control, in robust Kalman filtering, and reinforcement learning, for example, robust contextual bandits. And for these applications, we ask you to, please look at the paper. We have a lot of these details and the proof, and I hope this was helpful. Thank you very much.